This is a pre-lab for Lab 7, in which you will be introduced to sequential logic. It's assumed that you are familiar with combinational logic, and the purpose of this video is just to introduce you to some basic ideas of sequential logic, getting you to think about it, helping you to have some basic understanding of sequential logic before you go into the lab, and also to give you some familiarity of the circuits that you will be building in the lab, particularly the main circuit you'll be building, which is a two-input Jeopardy switch. So the goal of this lab is both to introduce you to sequential logic and then, frankly, to give you something fun to build and to play around with it. So let me begin by kind of giving you a soft introduction to sequential logic from the vantage point of what you know now, which is combinational logic. So suppose we have a combinational logic circuit. And we have three inputs, A, B, and C. So the output, F, is equal to a combination of all present inputs A, B, C. So the operating term here is present. Okay, so F depends only on the instantaneous and current or present inputs A, B, and C. That is fundamental to combinational logic, and it is also what distinguishes it from sequential logic. So now if we have a sequential logic circuit, and I have an output, and I'll call it Q, and I have two inputs. I could have three inputs, but I'm going to put just draw two inputs here. Then Q is equal to a combination, in general, it's a combination of present and past inputs A and B. Okay, and actually the way that you design a combinational circuit or sequential circuit from a combinational circuit is really simple, and I want to just give you that basic idea now. So if we go back to our combinational circuit that has an output and has three inputs, A, B, and C. If we add feedback to our combinational circuit, meaning that we take the output and in some way we return it to the input and connect it to one of our inputs, such that the original output, F, is not only a function of the inputs A and B, their present state, but also a function of the actual output, then you can get you can set up basically this chicken and egg. You know, it's basically this feedback that says whatever state the output goes to now becomes a state or a logic level that goes back to the input, and that might actually what we might latch the output to a particular state such that it remains at that logic level even if the inputs A and B should change. So let me demonstrate that to you with a simple logic circuit. Okay, we're going to take two NOR gates. Here's an input A, here's an input, here's an input B. We're going to take the output of the first one and go to the second one. We'll call this output here Q, and then I'm going to call this input here C. Okay, so there's my there's my logic circuit. And what I'm going to add, this is a combinational logic circuit right now, right? This is combinational. The only thing that is going to render it into a sequential circuit is that I'm going to take the input C and I'm going to connect it back to the output. Okay? This changes the combinational circuit to a sequential circuit. And let's see if we can understand how. I'm going to redraw this circuit in a way that is a little more compact. And I'm going to rename these inputs. I'm going to call this A, I'm going to call it S. I'm going to call this input B, call it R. And then I'm going to draw, actually let me redo it this way. Boom. Okay, so stop the video if you need to for a moment just to convince yourself that this circuit is the same circuit as I had before. This is equivalent. Okay, so let's draw a truth table for this. Okay, so we have S, R, and Q. Q is the output, S and R are the two inputs. And let's think about the NOR gate, for the logic for the NOR gate. The NOR gate, if either input of a NOR gate is high, okay, then the output is low. If either input of a NOR gate is high, then the output is low. So I can already fill a couple of these in pretty easily. Let me go ahead and do the sequence here. Oops. And so if S is, let's see, if R is high, if R is 1, then the output of that NOR gate being Q is going to be low. So this will be low. This is due to R equal 1. All right. Now similarly, let's see, what else can I say? If both of them are high, right here, then I also know that Q is going to be out low again because of R being equal to 1. Okay. Now, let's see, if S is high, let me call this, and this will make sense in a minute. Let me call it Q bar. Okay. If S is true, then Q bar is going to be false. All right. Q bar is false. And if Q bar is false, okay, now let's redraw this circuit just to clean it up. It'll be the equivalent circuit, but I'm going to just rewire or relay out the wires. So we have input A. I'm going to call that S for reasons that will be apparent in a little bit. This input B I'm going to call R. Take the output of the first NOR gate, send it to the input of the second. The output here we'll call Q, and then the output of Q goes back to the input of the first NOR gate, and we'll draw that in this manner. There's this symmetry about the circuit that is now apparent, and I'm going to call this, although this is not, I don't have to define this one, it's useful, call it Q bar, and that'll be, although we can leave that off for now, you can still think of this as having two inputs, A and B, or S and R, and one output Q. Now let's fill out, see if we can fill out a logic table. So we have S and R, and we have Q. And we could put Q bar here. I don't know if we'll need that. So let's leave that off. 0, 0, 0, 1, 1, 0, 1, 1. Let's see what we can fill out readily. A NOR gate is going to be false whenever at least one of the inputs is true. Okay, so that means that if R is true, then Q is false. Right? This is due to R being equal to 1. We can say the same thing here when both S and R are equal to 1. Right? Again, due to R being equal to 1. Now what about when S is equal to 1? All right, when S is equal to 1, then Q bar is going to be 0. Right? And Q bar now is fed to the first input of the second NOR gate. And because R is also at 0 at this point, we have the condition that, let me write this out, if S is 1 and R is 0, then we're going to have 0 here, and that means we have 0 at both inputs of the NOR gate, and therefore we have a 1 at the output. So we can write, let me erase all of these. And we'll write Q is then going to be equal to 1. Okay? Now what we don't know is, the last one that we don't know is when both S and R are equal to false. What do we actually have? Well, let's kind of play that out. If I have 0 for both of these, then Q bar will be equal to, it'll be equal to 1 if Q is equal to 0, right? Because if Q is equal to 0, I have Q back over here. And it's going to be equal to 0 if Q is equal to 1. And we can write that Q is going to be equal to 1 if Q bar is equal to 0, and Q will be equal to 0 if Q is equal to 1. This is when S and R are false. So you notice that when S and R are both false, the output Q does not even depend on S and R. That's the key thing. So we can write here, Q does not depend on S or R. Okay, in fact, what it depends on is the previous state of Q. So we actually have two scenarios here. We have, it could be, if previously we had that S was true and R was false, in other words this case, then Q would be equal to 1. So let me write it this way. I should expand this if I can write it to it. It would be 1 if previously S had been equal to 1. And it will be equal to 0 if previously R had been equal to 1. Alright, and herein lies the uniqueness of a sequential circuit relative to a combinational, is that you can actually have two different outputs, either true or false, for the same given input. So you'd never have that in combinational logic. You'd never have the scenario of when the two inputs are low, you could have one of two valid output states. But here you do, and it's based on the previous history. So let me draw. Let's actually see if we can kind of play with this a little bit. I'm going to draw a time chart, a graph for S and R and for Q. Okay, and Q I'm going to draw as being, this is low and low, drop it 0, 0, 0. This is 1 and this is 0. I don't know what Q is initially, but let's do this. Let's say that at some point S goes high. All right. Whatever Q was, at that point, Q is going to go high. Okay. So I don't know if it was high or low before. I really don't know. So maybe I should draw it this way. Because again, when both inputs are low, the output Q depends on some previous history. But I do know when S goes high and R is low, Q goes high. And notice that it remains high even after S goes low. Now let's say at some later date R pulses high. Okay? So at this point Q is going to be reset, and it's going to stay reset. If S pulses a little bit later, then it goes high again. Okay? So what you have here is S stands for set, and R stands for reset. So when S goes high, you're setting Q, and when R goes low, you reset Q. And actually it's the opposite. You can say reset, or you can say clear. Reset, clear. Here you're resetting Q bar, and here you're setting Q bar. If you look at the logic, you can go back and look at the circuit. You'll see that Q and Q bar are always inverses of each other logically. Okay, so that's this is called an RS flip-flop. Okay, RS flip-flop, a flip-flop. Okay, and it has an R input and an S input, and it has an output Q and typically an output Q bar. And you can implement this in a number of different ways, but in the end, functionally at an abstracted level, as a sequential circuit, it operates according to this this truth table right here, with the caveat that when both inputs are low, Q depends on the previous history of the inputs. Now you might wonder, what about when both are high? Okay, when both are high, then the output goes low. Now that can be used perhaps advantageously, that if you want to start the system with a known state, if you set both S and R high, then it actually will go to low. But usually, I mean, that has limited benefits, because when you turn both of those to low, one of them is going to go low a little bit sooner than the other one. So you might as well, if you want to go to a known state, it's better just to either set the S input high or set the R input high and get the output to a known state. And then you typically don't want both inputs to be high. Okay, this is the most simple flip-flop. There are other flip-flops that are built on this, where there's some more logic that's added around it that deals with avoiding the situation where you might not know what happens when S and R both go high, and it can avoid that situation. In this simple implementation, you don't want R and S to both be high. Generally, you want to have them resting at low values, and then you pulse either the R or S high in order to set or clear the state. Okay, so there's an introduction to the RS flip-flop. You're going to build two versions of the RS flip-flop. One as a NOR gate, and that's shown here on the left. You're going to put an LED on the output. You add a resistor R5 there to just current limit, because these little logic circuits are not able to supply lots of current. Plus, if they could, you wouldn't want to supply too much current to the LED, so you put a resistor in series to limit the current. So if this logic, for instance, goes to if the logic output here goes to, say, 5 volts, right? And if the on voltage of this LED is approximately, let's say, 2 volts, then you have 5 minus 2, or 3 volts across the resistor, and therefore you have 3 volts over 1K, or 3 milliamps of current, and that's how you limit the current to the LED. Also, the R1 and R2 at the input, notice they're much larger values, 20K. They're grounded, which basically ensures that by default the two inputs are at a logic low level when nothing is connected to them, and that's the state we want to rest in. So what you do is, if you have some wire and you just take that wire and touch it to S, that's like the pulse, that's like this pulse here, where you're going to set the flip-flop and you should see the LED turn on. If you now take your wire and you connect it over to the reset, pulse it, then you should see the LED reset. Okay, that's the whole purpose of this first circuit, is just for you to experience an actual sequential circuit. By the way, this is the building block for memory. So you can save a bit, 1 bit of information in this little cell. This is called, this would be the type of memory that would be referred to as static RAM. There's also what's called dynamic RAM, but this is static RAM. On the right here, this is the second circuit you're going to build, and it is also an RS flip-flop, but it is implemented discretely. So I wanted you to experience being able to construct a memory circuit using just discrete transistors. So this right here is a NOR gate, okay? And if you think of it, if either input of this, if this input here or this input go high, then that respective transistor goes on and pulls this output to 0, right? So that's a NOT function, a NORing function. So you're going to build that circuit, which will function just like the NOR gate implemented one on the left, and also just give you some practice using MOSFETs. The main circuit you're going to build is this Jeopardy switch, okay, this Jeopardy switch circuit, and I'm going to give you just a very quick tour of it. I see that I have to head to class in just a minute. So here's the basic idea of a Jeopardy switch. You have 2 switches right here, and you have 2 competitors, right, assigned one to each of these switches, and on some signal or upon answering, and they jump for a question or whatever, they'll push their button. And this circuit basically will tell you which contestant won out, which one pushed their button first. So if contestant A went first, then you'll get LED A that's going to turn on, and if contestant 2 pushed their button first, the LED 2 or B output will turn on. And then what will happen is, when the 2 contestants cease to press their buttons, the winning LED remains on. So there you have the memory function, this latching function of the RS flip-flop that will basically store in memory, if you will, which contestant pressed the button first. You then have a reset switch here that essentially clears the 2 flip-flops and turns off the 2 LEDs. Okay, so here's how it works in essence. You have, and I'm not going to explain all of it because I want to leave some of this discovery to you, but here are 2, this is an RS flip-flop. Okay, notice that the output of each of these RS flip-flops, this is going to be A, and this is going to be flip-flop B. The output of each of these is what drives the LED. So when Q of the respective flip-flop goes on or goes high, that respective LED will turn on. Okay, and if we just follow the logic, say from button A, if it goes into this AND gate, which you have yet to figure out why there's an AND gate, but assuming that this input at pin 2 is high, then whatever state the input A here goes to, if it goes high, then SA, the output, will go high. And if it goes high, this is like the setting bit or setting input to the RS flip-flop A, and so the corresponding LED will then go on, and that competitor wins. Okay. However, there's a caveat, because that contestant can only latch their flip-flop if this input is high. And this is the mechanism by which if the other contestant has pressed their button first, what you want is for the first contestant's flip-flop to be, or switch to be, locked out. All right, and that's the purpose of this AND gate here. So I'll let you figure that out. Now, the one other piece is that in the reset, you notice that these this input switch goes to the R input for each flip-flop. So that makes sense. When you press that button and it sets R high for each of those flip-flops, their corresponding outputs go low, the LEDs turn off. But in addition, there is this little circuit here, which basically is a mechanism for being able to turn on an LED that says ready when the system has been reset. So the idea is you don't want to ask the next question and have the contestants jump or press their buttons if the system has not been reset. So the ready light comes on to indicate that it is ready, the system is triggered, or armed, if you will. This could be viewed as an armed LED. So I'll stop here, let you figure out the rest of this, but I think you'll have fun building this lab and playing around with this. So